Okay, in this lesson we're going to look at trigonometric ratios and special angles. So before we do that, we're going to review terminal arm diagrams. So remember, to create an angle, you need two rays. These rays are called the initial arm and the terminal arm. So the initial arm and terminal arm both start at the positive x-axis, and then depending on the size of the angle, the terminal arm is then rotated counterclockwise. So you start this way and you rotate it counterclockwise. According to the value of the angle, placing it in one of the four quadrants that you see here. So if it's between 0 degrees and 90 degrees, then it'll be in quadrant 1. If it's between 0 and 180, if it's between 90 and 180, it'll be in quadrant 2. Between 180 and 270, it'll be in quadrant 3. And then from 270 to 360, we'll take you back to quadrant 4. Okay, so just a review of terminal arm diagrams. So when we examined terminal arm diagrams last year, what we talked about is how all the angles in the different quadrants are related to the related angle in the first quadrant. So as long as you knew the related angle in quadrant 1, you were able to solve for the corresponding angles in quadrants 2, 3, and 4. And the methodology we use in order to solve those is in quadrant 1, whatever the angle is, that's your related acute angle. In quadrant 2, if you knew the related acute angle, you would do 180 minus that value. In quadrant 3, because it's more than 180 degrees, you would add the related angle. And in quadrant 4, because it's just under 360 degrees, you would subtract the related angle from 360. So you can see that here. Now, because in this course you're looking at radians, you can do something very similar to that, except now we're going to be looking at it in terms of radians, and this is your greater focus that you want to pay attention to. So, if you end up with an angle that's in quadrant 1, your angle is the same as your related acute angle here. If you have an angle in quadrant 2, well, you know that all the way up till here, this is equal to 180 degrees, or pi radians. And so if you're trying to find an angle in quadrant 2, in order to solve for that angle, you would do pi minus whatever the related acute angle is. Okay, so to find an angle in quadrant 2, that's what you would do. Okay, in quadrant 3, because it's a little bit more than half a rotation, you would do pi plus the related acute angle. And then in quadrant 4, same idea, a full rotation would be 2 pi radians. And so because you're looking for an angle in quadrant 4, you would do 2 pi radians minus the related acute angle. Okay, so these are the new ways for you to figure out the angle in any one of the four quadrants. So some more things for you to remember from last year. Remember the reciprocal functions that we looked at. So we know the primary trig functions, which are sine, cosine, and tangent. And we know the reciprocal functions are cosecant, secant, and cotangent. So you can see here the relationship between sine and cosecant, and the relationship between cosine and secant, and the relationship between tangent and cotangent. They are all reciprocal functions. And so when you're looking at them, for sine, normally you would do opposite over hypotenuse. For cosecant, you would do hypotenuse over opposite. Okay, so reciprocal meaning you literally switch the numerator and denominators. Okay. Also from last year, what you want to remember is the cast rule. There we go. Okay, so remember when we looked at sine, cosine, and tangent last year, we looked at it in terms of x, y, and r. And so we use that to help us figure out why the cast rule actually works. And so the cast rule is just a quick way to see which quadrants the trig ratio is positive. So remember the way cast is spelled, C-A-S-N-T. And all it meant is in that particular quadrant, that particular ratio was positive. Okay, so in the first quadrant, all the ratios are positive, which means sine, cosine, and tangent are all positive. In quadrant 2, only the sine ratio is positive, which means cosine and tangent are negative. In quadrant 3, tangent is positive, which means sine and cosine are negative. And in quadrant 4, cosine is positive, which means sine and tangent are going to be negative. And the reason why that happens is because of the sign of x and y in each one of those quadrants. So you can see here if x and y are all positive, then what you end up with is positive over positive for sine, positive over positive for cosine, and positive over positive for tangent, which results in a positive ratio for all three of them. But in quadrant 2, the reason why the sine function is the only one that's positive is because in this quadrant, the values of x are all negative and the values of y are all positive. And if you think about what happens when you plug in those particular signs for x and y into the sine, cosine, and tangent ratio, it'll make it a little bit clearer as to why those ratios are positive or negative in that quadrant. So the sine ratio is y over r. Y is positive in quadrant 2, as you can see here. And r is always positive because it represents a radius for a circle. And so that ends up getting a positive over a positive, which means your ratio ends up being positive. Whereas for cosine, x is negative, r is positive, which means a negative over a positive will give me a negative result, and so the cosine ratio will be negative. Same thing for the tangent. I have positive y values but negative x values, and a positive divided by a negative value will give me a negative result, which is why tangent is also negative in this quadrant. Okay, and the same goes for quadrant 3 and for quadrant 4 as well. Okay, so some more things for you to remember are the special angles in degrees, and we're going to be looking at them in radians shortly. So last year when you looked at the special angles, we looked at two special right triangles, and they allowed us to find the exact values of primary trig ratios for the special angles 30, 45, and 60. So we had two triangles, the 45, 45, 90 triangle and the 30, 60, 90 triangle. And so this year, because we're looking at angle measures in radians, we're no longer going to be looking at 45, 45, 90 and 30, 60, 90. We're going to look at those angles in radians instead, and you'll see that in a few minutes. Okay, so just as a quick little reminder, the 45, 45, 90 triangle was the isosceles triangle, and so it had two equal side lengths, so these two sides were the same. And then to find the third side, you just need to use Pythagorean theorem to help you solve it. And then you have the 30, 60, 90 triangle. So small angle is across the small side, medium angle is across the medium side, and then the largest angle is across the largest side. And again, the 2 and the 1 here are easy. To find this side, you can just use the Pythagorean theorem. Okay, so they are right angle triangles, so Pythagorean theorem holds true for both the triangles. So what we're going to look at now are the cast rule with radians instead of looking at it in terms of degrees. And then we're also going to look at the special angles in radians as well. So the cast rule with radians, if you take a look at the cast rule, it's still exactly the same. The only thing you need to remember is that instead of looking at this as 90 degrees, 180 degrees, 270 degrees, and 360 degrees, and now you're looking at the angle measure in terms of radians. And so pi is 180 degrees, so we know this is a half a rotation. So full rotation would be double that, which would be 2 pi. Okay, half of a rotation, so 1/4 of a rotation, if you will, would be pi over 2. So this is equivalent to 90 degrees. And then 3 pi over 2 is equivalent to 3/4 of a rotation, which would be 270 degrees. Okay. And so the way you look at the cast rule is exactly the same, except now instead of degrees, you're looking at radians. Okay. So what this means is that the sine ratio is still going to be positive from 0 to pi over 2. And it'll also be positive for any angles that go from pi over 2 to pi. So this is just a set of angles that the sine ratio will be positive for. The cosine ratio will be positive in quadrant 1 and quadrant 4. So that means any angle between 0 and pi over 2, and between 3 pi over 2 and 2 pi, you'll get a positive value for the cosine ratio. And finally, for the tangent ratio, tangent's going to be positive in quadrants 1 and quadrant 3, which means from any angle from 0 to pi over 2, and any angle from pi to 3 pi over 2 will give you a positive ratio for tangent. Okay, and then we're going to look at the special angles in radians now. So remember that in 45 degrees is equivalent to pi over 4, 30 degrees is equivalent to pi over 6, and 60 degrees is equivalent to pi over 3. Okay, and in case you forgot how to do that conversion, it's really easy. You're just multiplying it by pi over 180, and then it's just a matter of reducing it, and so this would give you pi over 3. Okay, so in case you forgot how we went from degrees to radians, we just used a conversion factor, and in this case it's multiplying by pi over 180. So the two special triangles you examined last year can be rewritten now using radian measure as follows. So this is what used to be our 45, 45, 90 triangle, and now it's our pi over 4, pi over 4, pi over 2 triangle. Okay, and you can see that the side lengths that correspond are exactly the same. In the same way, we used to have a 30, 60, 90 triangle. Now it's pi over 6, pi over 3, and pi over 2. And you can see again the side lengths are exactly the same. So what you need to remember is now instead of looking at it in terms of degrees, we're looking at it in terms of radians. Okay, we're going to look at a few examples. So our first example asks us to evaluate the following as exact answers. So the fact that it says exact answers tells me I'm looking at my special angles. And so I'm looking for a sine of pi over 6. So the first thing I'm going to do is actually use my special triangles. And what I've done here is I've drawn them on a sticky note. So it makes it easy anytime I need to do a question. It'll make it quick and easy. So if I'm looking at sine of pi over 6, I'm going to look at the special triangle that includes pi over 6. And I'm looking at the sine of it. So I'm looking at the opposite side versus a hypotenuse, which would give me 1/2. And that's all you're doing there. You're just looking at what the ratio would be. Then I'm looking at the secant of pi over 4. So I'm going to look for my pi over 4 angle in my special triangle. So that's this one here. It's the isosceles triangle. And so for the pi over 4 angle, I'm looking at the secant. So normally, this is actually the reciprocal of cosine. So what I'm going to do is instead of looking at adjacent over hypotenuse, I'm going to look at hypotenuse over adjacent since it's a reciprocal of cosine. So hypotenuse over adjacent would give me root 2 over 1. And that's it for that one. Or you can rewrite this as root 2 as well. You don't have to write over 1 if you don't want to. And then finally we have the tangent of pi over 3. And so I look for my pi over 3 angle. And tangent looks at opposite over adjacent. So opposite over adjacent gives me root 3 over 1. Or I can just write this as root 3 as well. Okay.